All right, here we go. So, just to recap what we were talking about today, we're going to finish what we need for regression. Thursday, I'm going to make the final exam review day. Okay, I'm going to give you an outline of all the types of questions to be prepared for, right? And just kind of guide your studying a little bit. Okay, so final exam review day. Oops, that looks like a woo. There. I'll highlight that because that's kind of a twist. I think on our Moodle page, it says that's on Friday, but then that got too tight. I also, usually for the final exam review, what I like to do is make a kind of a tree diagram, a decision tree for your hypothesis testing, where we outline all the conditions and all the different tests that we've done so that you kind of have a clear overview. And I'll bring larger size paper because you'll need a lot of space. Okay? Yeah.
Are you gonna use like a
Practice?
yeah?
Yes. So I'm thinking that's what we'll do on Friday. Is I'll have posted a practice final. Okay. Practice final exam review is what I'm leaning towards. 50 minutes isn't really enough time to review a 3-hour exam. It's more like a 2-hour exam. So usually you get 3 hours, but it would still take probably 2 hours pretty reasonably. And so it's not really enough time to do it, but we can look at all the questions and we can kind of pick out some that that we're more worried about. How about that? All right. Any questions about that? No. All right. Quick review. Right. We talked about the least squares of regression line and how we get it. B0 plus B1x, right? Where B1 is the slope, which is R times SY over SX, which is the slope. I hope I don't have them mixed up. And B naught is Y bar minus B1 X bar. This one I'm going to have to look up the y-intercept. Okay. Let's see on our formula sheet. SY over SX, phew. Y bar minus B1 times X bar, phew. So I did it. We talked about how do we solve for the slope? How do we find the intercept? For these regression lines, given all that information that we need, okay? And so what we finished, we were talking about this gift aid example, feels like a long time ago, where we were talking about the amount of gift aid that a student receives based off of their family income, right? So as the family income is increasing, the amount of gift aid that you would receive is decreasing, right? So we've got this negative relationship. And so then we were given this information here, and we were able to use that to calculate the slope and the intercept. So we calculated the slope and we found that it's negative 0.043. And then we found the intercept, 24,327 and 72 pennies, because it's in money, right? And then we kind of ended here. We're going to pick up where we left off. Continuing the gift aid example from last day. We were told to, or I told you, construct the least squares regression line, which is something that you're going to have to do. And then we said, okay, a main goal, and what I'll do is I'll just kind of bump this down and say end of review there. I had to call it at some point there. The main goal of constructing this regression model, right, is to be able to predict future values of y, right? So here, this is the predicted gift aid, right? And so now what we can do is we can use this to put in some family income, and then we can do this calculation relatively easy with a calculator, obviously. But then we have the predicted gift date. Right? And so let's predict the gift aid. Let's see here, constantly jumping around. Something else I wanted to do. I don't have anything. Okay. Predict the gift aid of a student whose family income is 100,000 per year. I'll put it on its own page here. There. So then, just stealing this because I don't want to type or write it out again. Okay. What we're going to do, oops, is erase all this there. Now we have family income. One thing, especially when we're dealing with large numbers, usually we scale them down and talk about it in thousands and things like that. So what we want to do is just check against the, hey, did I start the recording? I always have a panicky moment. Okay, good, I did. What a time to forget. Last week. Classes. So here, these values are in the 100,000s or in the thousands. And so 100,000 is in here. And so what we can do is we can just plug in 100,000. But I know a lot of the questions that we talk about, it'll be in thousands. So then you would put in 100,000 and kind of convert back and forth. But this one, it's in 100,000 already. Oh, wrong day. There. So we are good to go. So then what we're going to do here is we have 24327.72 minus 0.0431 times, and then we plug in the family income, which we're told we want it to be 100,000. So then if I do this calculation, I get 20,016.71647. If I round to 2 decimal places, I get money. 20,016 and 72 pennies is the predicted amount of gift aid for a student whose family income is $100,000 per year. Nice. All right. So that's going to be our main reason for making this line, is to be able to predict values, predict the gift aid without having to look at actual data. Right now you can take away that data that we built the line from, and we can still use it to predict how much gift aid you would get. Okay. The next thing is that we need to be able to interpret the slope and interpret the intercept, right? Yeah.
Sorry. If we have the slope, would it not just be easier to use it to continue on and graph to that point?
Do you mean here? I'm not sure what you mean.
Well, like if we have,
Because here we use the
and
slope.
X value,
Yeah.
can't we just graph that to find what value, what value things get?
Oh, but that's what we're doing with this equation here,
Oh, okay.
right? Because technically it's just y hat is equal to the y-intercept plus, technically it's plus the slope, but it's a negative slope, so that's why it's negative, times x, right?
And then this is just to make sure that we can get an exact value rather than like a close estimate.
So this is our, so the hat makes it a predicted value, right? And so from the scatter plot, we see that the actual values that we have in our data set, they're all over the place, right? But this is our best prediction that we can come up with.
Yeah, I think it's just because if we look at the graph, it's like bang on 20K, which is basically what it is. So how is this being predicted from that?
Okay, so,
Sorry.
no, it's okay. So here, this line, just ignore the dashed line. It's really stupid that they had it. This is, the dashed line was the one that they fit by eye. It's really weird. Just ignore that. Just look at the solid line. Okay, but if we have 100,000, then here, what this is at this line. So here, let's see if I can just grab this and bring it in, because that's exactly what we've done, right? We put in X equals 100,000. And then on this line, it puts us at 20,016.72 at Y. So the line is the predicted value. Does that make sense?
Yeah, it's okay. I'm just thinking it.
Okay, so, but what we found is the equation of the line.
Okay.
Right.
No, that makes sense. Yeah.
So then, so it will be the same.
Okay.
Yeah. But we need to use the equation because you don't want to be eyeballing it, right? Whoops. You actually want to have an actual true value. Your best prediction.
Okay, yeah. I think that's what I was looking at.
Yeah.
That makes sense.
Nice. Okay, so like I was saying, we need to be able to interpret the slope and interpret the intercept, just in case someone asks us, hey, what is this line? What does it tell me? Okay, and so we need to be able to interpret the slope and the intercept. Whenever I say intercept, I mean the y-intercept. The x-intercept, it's not really that useful. Okay, but let's start with the slope. The general interpretation of the slope is this. And it's one of those things that I make you memorize, and eventually, once you've memorized it enough, it'll just roll off your tongue. For each unit increase, in X, we will see a slope increase. And I know you guys aren't going to like this because the slope could be negative, it could be positive. But if you say increase, a negative increase is a decrease, and then you don't get caught up in kind of interpretation too much. Okay, so if you always say increase, even though it sounds weird, it'll always be true, and that's the most important thing. So we'll see a slope increase in the predicted value of y. Okay. So here I'll do a little explanation. Okay. So even if the slope is negative, we can still say increase. Right, so here, as an example, a -4 increase is the same as saying a 4-unit decrease. Okay. The problem is if you're using terms like decrease instead of increase, then if you keep the negative on there, a -4 decrease is actually an increase, and so then you're wrong, right? And so you have to be really careful. So that's why for me, I just say a -4 increase. It doesn't sound good, but it's true, right? Whereas here you would need to drop the negative. Just little picky things, right? But it is important that everything we say is true, right? So I always say just a slope, and maybe you can throw in unit increase if you want. But the unit increase is the most important. So for each unit increase in X, okay? And if you look at your regression line, y hat is, well, it's b0 plus b1x, okay, in general, right? And so what we have is, okay, well, the slope, if you look at it, how it interacts with your x and your y hat is that for each unit in x, right, as x goes from 1 to 2, 2 to 3, 3 to 4, right, then the predicted value of y is going to increase by the slope amount, right? And so I use this equation just to kind of guide my interpretation, right? If I have to interpret the slope, right, then I know that as x goes from 1 to 2, 2 to 3, 3 to 4, right? For each unit increase, the intercept stays the same, right? It's just a kind of an anchor, right? And then what we have, if we use our regression line, where do I have it? 24,327.72 minus 0.0431 times x, which is the family income. Right. Family income and gift aid. It's up to you whether you like to use the actual variable names in there or just y and x is totally fine as well. Just have to figure out what helps you. So if we had to interpret the slope, for each unit increase in family income, right? So for each unit increase, and this is where it would be important to know what the units of family income are, right? Is it in dollars? Is it in $10,000? Is it in thousands of dollars, right? Doesn't, in this case, it's just per dollar, right? So for each unit increase in family income, let me use the we will see a negative 0.0431 unit increase, which if you're fancy, you can say a 0.0431 decrease, but I'm not. Increase in the predicted, maybe I'll say unit, increase in the predicted gift date. But notice how I just took the general interpretation, right? For each unit increase in X, for each unit increase in family income, we will see a negative 0.0431 unit increase in the predicted value of gift date or the predicted gift date. Right? So you just replace your X with your X and your Y with your Y and your slope with your slope, then you're done. Good. And I don't expect you to go for kind of the unit increase for each dollar increase or anything like that. You can just stick with for each unit increase in, but I want to see you exchange the X with what the X variable is. Right. All right. Questions about that one? Oh. Okay. Let's talk about the intercept, the y-intercept. The general interpretation of the y-intercept, right? The y-intercept is and I always go back to this equation again, right? It's the predicted value of y when X is 0, right? So if I set X equal to 0, then the y-intercept is the predicted value of y, and that is the interpretation of the y-intercept. So the y-intercept is the predicted value of y when X is 0. Okay. So the things that I'm looking for when I'm marking these interpretations, because that's really what we're here for now, I guess, is the y-intercept. You have to talk about X being 0, right? It's the predicted value of y when X is 0. Okay. Here for the slope, it's the unit increase in X, right? For each unit increase in X, right, we'll see a slope unit increase in the predicted value of y, right? But those are the two things. So how X interacts with the value, right? And how it impacts your y hat. That's what I want to know about. Yeah. And so here, if we want to interpret the intercept. So for example, and maybe I already had example. I did. So I don't need two examples. Interpret the intercept. The predicted gift aid for a student whose family income is $0 per year is $24,327.72. Right? And so the predicted gift aid for a student whose family income is $0 per year is $24,327.72. Right? It's the predicted value of y when x is 0. Sometimes as a follow-up, I'll ask you if the intercept is meaningful, because like we said, the intercept is just an anchor, right? It's just what is the value of y? Of course, a straight line goes from -infinity to +infinity, right? You can use this line forever for any value of x, but there's only a certain range of x, right? The x's that you've used to build this line, that's really the only place where this line applies, right? So lines just inherently just go forever, right? We could use it forever. But when we go beyond the range of our data, right, the values of, and I say range, but if you're from I got some math people here, you guys are going to be going nuts, right? Range is usually for y. So I should say what? The domain of the data. Right. And so, but for some reason we call it the range, makes no sense, whatever. It's the values of x, right? So this line is really only meaningful for these values of x. Yeah? So as a follow-up, I'll usually ask, is the intercept meaningful? Yeah? So is the intercept meaningful? Oops. This is where you're going to argue if x can reasonably be 0. And so here, it's basically asking, can x reasonably be 0? Is what's understood there. Okay. Now, there's no wrong answer. Usually there's kind of a more right answer, right? And what I do when I look at these, when I have to answer a question like that, is I look and I see that a family income of 0, there are values where there's 0 family income, right? And so I've got dots that are relatively close to 0, right? And then all the way up to, let's say, 300,000, right? And so this line applies for family incomes between 0 to 300,000, right? Does it apply to someone's family who makes, let's say, $1 million a year? No, right? You probably get no income or no gift aid. I am guessing what would happen with the line is you would get a negative predicted gift aid, which makes no sense either, right? And so it only applies to these values of x. Okay. So here, what you do is there's no wrong answer. But must argue whether x can be 0. if x equals 0 is, oh, I don't know why I wrote 100 there. Wishful thinking, I guess. If x equals 0 is included in the data set, right, or close, right? In this case, it's probably close. Okay, so if x equals 0 is in the data set, it can be 0. So the y-intercept is meaningful. Usually if we're doing things like predicting house prices, right? If we set, if we're talking about the square footage of the home as our explanatory variable, right? I make the home 0 square feet. Is that meaningful? You could say yes, because that should be the lot value then, right? Or no, because a home with 0 square feet doesn't exist, so it's not worth anything, right? It just depends on how you're feeling that day, I guess. But you have to argue if x can be 0 or no. But there's no wrong answer. It's just your argument has to come from x equals 0.
So then, if we decided that it's unreasonable for x to be 0, does that basically shift our y-intercept according to whatever?
No, because the y-intercept is the y-intercept, right? It's just where it crosses the y-axis, right? And so, but that's because the line, right, it goes on forever and ever and ever. And so it's going to cross the y-axis at some point, right? And so it doesn't, it's only meaningful if it's part of the data set, right? But if it crosses way out, you know, kind of way earlier and on the x-axis, then it's not meaningful, right? It's just what the prediction is when x is 0, but it doesn't mean anything. Does that make sense? All right. So now this leads me to extrapolation. Extrapolation is when we use the model to predict values of y outside the range of our data slash domain of our data, I guess. Sorry, guys. Okay, so extrapolation is when we use our linear regression model to predict values of y using x values beyond the range of our data. Sorry, I can't seem to shake it. Using values of x beyond the range, and by that, I guess I mean domain of our data. So here, let's see if I have it. Nope. But I'll grab it. Beep. Paste. Okay, wait. Okay. Let's see here. So here, and there's some wiggle room, right? Because maybe we just didn't see 300,000 in our data set, but it's reasonably close, right? You can't have a negative family income, right? Let's just agree to that, right? But here, the range of the data, range or domain of the data is from 0 to roughly 300,000 per year in family income. Right. So when we use this line to make predictions using values of X outside this range, that's what we call extrapolation. Now, the problem becomes sometimes that is the only thing we can do, right? But it makes our prediction less reliable. How do I write that all down? Need some sort of dictation device here. What did I say? Okay. We can use the regression line to predict values of Y outside the range of the data. And sometimes it's still our best prediction. Okay. And sometimes it is our best prediction, right? It's the best thing we've got. But when we are extrapolating, our predictions are less reliable. But when we are extrapolating, our predictions are less reliable. Let's see here. Okay. I rarely bring it up, I guess, but I have it in my notes here. When you go beyond the range of the data, so beyond these X's, then it's called extrapolation. If you're predicting within these values, it's called interpolation, but that one's less important because that's what you should be doing, right? So we don't need a name for it, but extrapolation is bad. And usually I'll show you the type of question that I usually ask. I say, predict the gift aid for a family who makes 600,000 a year, right? And then I usually have a follow-up. Do you trust this prediction? And then there's often little scribbles saying, no, I don't trust this prediction because of the word that I can't remember right now. They mean extrapolation. Close enough, I say. Get pretty generous when I'm marking the final exam. Oh, there's that word. I don't know. I don't remember. It's like, yeah, well, you knew what to say. That's good. All right. So, for example, predict the gift aid for a student whose family income is, let's do 600,000 a year. I don't have it. Hey, I've got 1 million. You guys want to do 1 million? I've got it all calculated out, so let's do that. Whose family income is 1,000,000 per year. Do you trust this prediction? Poking you in the right direction. So I've got the predicted gift aid. That doesn't look like a hat there. 2432772 minus 0.0431. I acquired a 1 at some point. these might be slightly off because I don't have the rounded values here, which is kind of sneaky of me, I guess. Close enough though. Put in 1 million. See what we get out here. Oh, this should be family income, but I don't want to write it out again. I get a predicted gift aid of negative 18,782 and 28 pennies. Although, like I said, in my work, I have non-rounded values here, so a little sloppy, I guess. This doesn't make sense. Do you trust this prediction? No, because we're extrapolating beyond the range of the data, right? 1 million is not on our x-axis. Right? It's way out. No, I do not trust this prediction. Because x equal to 1 million is not within the range of the data. Therefore, this is an extrapolation. It's your best prediction, but it's not very good, right? But if you had to, this would be your predicted value. There's no reason for it to be anything else. I mean, there's maybe some truth to it. If you're making $1 million a year, maybe you're donating to the school, who knows? But I'm taking it too far, but you could start thinking of it that way as well, but we're not going to. Yeah.
You just call it zero because it's not like student aid would be like, oh, you make so much money, you actually have to pay us.
So reasonably it would be zero, right? You get no money, but the predicted value is this, right? Is the negative 18,000 because that's what the line is telling you, right? All right, nice. Doing it. We already talked about this before, but another question we could ask is, what percentage of variability in gift aid is explained by the least squares regression line on family income? Is explained by the least squares regression line on family income. This is where I wanted you guys to have this internal trigger, right? If you see proportion of variability, percentage of variability, right? Then you're thinking R squared, right? And we kind of jumped ahead and talked about it because we needed it. Okay. But R squared is the correlation squared. And the correlation, we were given it, what now? It's asking me to rate notability. No, I'm not doing that. Not right now. The correlation is negative 0.499. So here we had R squared is negative 0.499 squared. So we get R squared is 0.249001. This is a proportion, right? Just as a reminder from way back when, we were asked for the percentage. Now at this point on the final exam, if you left it as a proportion, it doesn't matter, right? But it's asking for the percentage of variability. So we convert it to a percentage and 24.9001%, right? This is a percentage. Nice. Okay. Good. Then we already did this and that and the other thing. I think it's important for you guys to see some output. Okay. Hey, I copied it. Copy. Paste. Okay. So regression output looks like this. So simple linear regression. Now simple linear regression, the simple just means you have one X. Okay. I'll show you output for a multiple linear regression. Now the linear just means that you're adding things together. Okay. And so you can have multiple values of X, but it becomes difficult to visualize, right? You can have more than one variable, but we can only really visualize well with just one value of X. So that's where we start. But after that, everything stays the same. Okay. And so here is the data that we had. Now, we were using rounded values of X, I guess. 24327, 24319, slightly different, right? But software is just going to use all the data. It's not going to do any rounding along the way. We use some rounding kind of willy-nilly. And so that's why our values are a little bit different. But let's just talk about the makeup of this table, especially these first two columns and two rows. Okay, so here, I'll do it kind of like the maps, where it's like, here's this thing blown up. It's the same stuff, okay? But what we have is the estimate. Now, this is the point estimate for the slope and the intercept, or other way around. Okay, so here, this is the point estimate for the y-intercept be not with our notation, and slope B1. Just as before, we use data, right, to get our point estimates, and then that's our best guess at what the population looks like, right? But in theory, we are estimating the population line, right? The population relationship, which would be y is beta naught plus beta 1 times x. Okay, and usually we use capitals here. That's the parameter version, right? So we use betas instead of b's. right? And so here, what we're doing is we're finding, we're estimating the population relationship with y hat is equal to b0 plus b1x, right? Where b0 is the point estimate of the population intercept and b1 is the point estimate of the slope, population slope there. So there is that going on. We don't need to worry about it too much, right? But what's happening is, okay. The rest of this output, we have the point estimate. Okay. We have the standard error of the point estimate. Okay. And then they've also calculated the t. Now, remember, a t is, I've got my point estimate minus my hypothesized value. How far is it from the hypothesized value divided by the standard error of the point estimate? Okay. Now, what we're doing here with the t is seeing how far it is from 0, right? Is the slope significantly different from 0? Why? Yes, why? A t of 18.83, and it even gives us the p-values less than 0.00, it's almost 0, right? Which makes sense, this is huge. It's not 0, that's not that interesting. Usually what we focus on is we wanna know, well, is the slope significantly different from 0, right? Because the slope of 0 looks like this, right? Just a horizontal line, there's nothing going on. So if the slope is significantly different from 0, then there is a relationship, right, between gift aid and family income. Okay, let's see if I can, I'm just gonna copy this, see what I can do here. Crop it. Okay. So here we have your point estimate. You have your standard error of the point estimates. And then you've got your T's. Now where T is going to be your point estimate minus 0 divided by the standard error of the point estimate. This 0, usually we get this 0, right, the hypothesized value from our null hypothesis, but now what we can do is we can kind of flip it and say, okay, well, from this, right, these p-values, now what color haven't I used? Let's do this one. These p-values then are testing a hypothesis, copy. So here we have the p-values. Now this top one is testing the null hypothesis that the y-intercept, the population y-intercept is 0 versus the alternative that it's not 0. Right? Not that fun, right? Here we're seeing is the y-intercept, I'll just say int, significantly different from 0. We get a very small p-value, so yes, it is. Not that interesting, right? But what's more interesting, let's use these colors I haven't seen before, right? I'll even say more interesting is testing if the slope is equal to 0 or if it's significantly different from 0, right? Since a slope of 0 means that there's no relationship, since a slope of 0 means there is no relationship between X and Y. Right? It would look like, so, oh, whoa. Oh, you guys can't see that. It's doing something very weird on my end. X and Y, right? No relationship. It's just a cloud. And my best line of best fit here, that doesn't look like 0 slope. Looks like this, just straight across. Still drew it poorly. Try again. Just go with it. There. That's better. Right. So this is what a slope of 0 looks like. So now we're saying, okay, if I get a small p-value for the slope, then I can say that, okay, family income is helping me predict the gift aid, right? It is contributing to the gift aid. From the R squared, it looks like there's a lot missing, right? The family income is part of it, but only 24.9% of all that activity is captured by just the family income. And so there are other variables that we can incorporate, right, to improve our fit. But that's what's going on. And so kind of fun, just like the other output questions we've seen, the ANOVA, right? If we have the p-value, all we really need to know is what the null and alternative hypotheses are, then we can just kind of go for it, right? And so here, with a p-value of 0.0002, that is less than 0.05, so the slope is significantly different from 0, right? And we're always doing a two-sided test, because why not? Okay. So that's how you would read and kind of understand the output. Don't worry, you don't have to do it on the final, but it is good for life things, because that's what it would look like if you're doing it, right? So you wouldn't actually have to calculate the slope or the intercept, but you do need to know how to read this output. Okay. All right. How much time do I have? I'll say in this case, we can conclude, well, I shouldn't spin it like that. Since the p-value of 0.0002, right, for the slope is less than the assumed alpha level of 0.05, we have enough evidence to reject H naught in favor of HA. Which means the slope is significantly different from 0, and I'll add in brackets because you could end there if you wanted to, but therefore family income is a useful predictor for gift aid. Right, it helps us in predicting the gift aid. Good. Doing it, guys. We're doing it. One thing that we haven't talked about that you have probably seen maybe is if we have a categorical predictor, so a categorical value of X, right? And so far, both X and Y have been numerical. But we can also use categorical values for X, or we can also have categorical explanatory variables. We can't have a categorical value for Y because then you should be doing classification, things like logistic regression. There are other things, but logistic regression is our go-to. Okay? And so then you're in a different kind of realm. Okay, so we're only predicting numerical values of Y, but we can have categorical values of X. Okay, so most commonly, categorical variables are given as binary variables. So binary meaning 0, 1. Most commonly, categorical variables are binary. In stats, we call them dummy variables, right? 0, 1. We've seen that before, right? With proportions, right? You have a success or a failure. 1 is a success. 0 means a failure, right? So all categorical variables can be turned into a series of dummy variables or binary variables, right? Because you either have a red shirt on or you didn't, right? That kind of thing. So there's one. Oh yeah, so funny. She says treacherous a lot. Extrapolation is treacherous. Feel like maybe 4 times in the textbook she says treacherous, which I think is pretty funny. But here, so here, if we have, we want to look at the total price for eBay auctions for the Mario Kart, for Nintendo Wii, and the only predictor that we have, so the only X that we have is whether it was used or whether it was new, right? And so then we have this numerical outcome, right? The total price of this video game, or yeah, video game. I don't know, I'm not well versed. Right, and so we have this numerical outcome, but just a binary predictor, right? Was it new? Was it used? And what we see here is that okay, well, it looks like overall, right, the price that you were able to charge for a new game was higher than a used game, right? And so here, and I'm just gonna copy. I cut one of the dots. Hopefully you'll survive. It's still there, but so here we have the predicted price, right? Because the price is the Y. And our X is this binary variable, whether it's used or whether it's new. And the line, the equation of the line is here, right? And with only two values of X, right, we can figure out what the predicted price is for both of those categories, right? If the condition new, which is just the variable that houses a 0 or a 1, right? If I turn that to 0, then the predicted price is 42.87, right? And so here, if we let X equal 0, right, then the game is used, then the predicted, price is 42.87 plus 1090 times 0. So 42.87. And if I let X be 1, then it's new. Then the predicted price is 287 plus 1090 times 1. So the predicted price is 53.77. So now we have the predictions for both of those categories, and that's really all we can do, right? There are other variables that contribute to the sale price, right, or the selling price, but as far as the new used condition, those are our predictions, right? So here, I'll just clarify that this is either 0 or 1. Okay. Let's see here. The very last section that we need to talk about is just different types of outliers. And I did that, those p-values looking at the output. I think that was jumping ahead maybe to 8.4. But like I said, I want you guys to have seen it at least. It's more important than the different types of outliers. So types of outliers in linear regression. Okay. So there are different types of outliers, of course, and a lot of it, or dealing with different outliers, is just going to come from experience, unfortunately. Okay. But there are a couple of rules of thumb that I want you to keep in mind. Okay. Let's see here. So just as before, we have the original plot up top, right, with an outlier here, and then we have the residual plots down below. Again, the residual plots are just magnifications, right? And so here it's just more obvious that you have an outlier, okay? And so these are the residual plots. And we have the original plots up top. So I'm going to go ahead and circle these outliers here because they are all different types of outliers. Okay, I might have this cluster, and this guy here. All right, Now, the difference between, I guess this one, let's look at plot number 2 and plot number 5. Okay. So here I clearly have a relationship here, right? And then if I extend the line, it's trying to capture this outlier, okay? It's not a concern so much, right? Because it's still in the same trajectory. Okay, so what you do is you imagine you remove this outlier and see how the line would change, right? And that is what you do when you're dealing with outliers. What do I do? Well, remove it and see what happens, right? If there's a huge change, you have a decision to make, right? If there isn't a huge change, then just keep it, right? You're always trying to keep as much data as you can. And so if you can, keep the data point would be my take home message. If it makes a huge change, like if we zoom in here to this guy here and just cover up this outlier and just focus on this cloud here, right? Is there any particular reason why the line would be so strong and so positive here? This just looks like a cloud to me, right? So without this outlier pulling the line towards it, there would be no relationship here, right? And so if we weren't careful, we would say, oh yeah, there's a super strong relationship between X and Y because I have this strong slope, right? But that's not the case. What's happening is the outlier is pulling that line towards it. Okay. So let's see here. An outlier is influential, we call it, if removing the points, potentially more than one, right? As we saw here, can be kind of a group of outliers, right? If removing the points changes the regression equation significantly, changes the regression equation significantly. So if we find our scatter plot has an outlier or multiple outliers, then your main goal is to keep as much data as you can, right? So I had a lot of friends in grad school biology, and they would just delete data. Oh, that one's bad, that one's bad, that one's bad, that one's bad. That's bad. You shouldn't do that. Okay, so if we find our scatter plot has, I'll say an outlier, but potentially more than one outliers, we keep in mind that we want to keep as much data as we can, that we want to keep as much data as possible. Whoops, moosh. Okay. So first thing you're going to do is you're going to fit the line with the outliers. Then you're going to remove the outliers temporarily. Then fit the line again. And then you're going to compare the slopes and the intercepts. Compare the slopes and the intercepts. Okay. Right. if there's a large change, we remove the outliers. There. Got a minute over. Yeah.
And that's done with an alpha level of 0.05 usually.
Yeah, usually that's safe. Unless you're working at NASA or something, 0.05 is usually pretty good. They like to be a little bit more sure, right? But yeah, I have this one example where it's catheter sizes. Things like that you want to be a little bit more particular about. But if it's just outliers, removing or keeping 0.05. All right, that's it. See you guys on Thursday. End this recording here.